Okay, so I'm going to do this problem. So we have the temperature distribution known. I want to give an expression for the total thermal energy content contained in a rod. Okay, so I didn't state this explicitly, but the way I'm going to do it is I'm going to assume that the rod is not homogeneous. Okay, so the area of the rod could vary, the composition of the rod could vary, so on and so forth. What I'm going to do is the following. I'm going to do the normal calculus thing, and I'm going to see, estimate the total energy in a thin slice, add all of those thin slices up, and then that becomes an integral. Okay, so energy in the thin slice. Okay, and we want to relate this to the temperature. Okay, so remember that the specific heat, which needs to vary because I'm assuming the rod is not homogeneous. So C of x is the specific heat. It is the heat energy that's required, or the thermal energy, I'm going to call it. The thermal energy required to raise, oh, that was supposed to be an R, not a P. To raise a unit mass 1 degree. And again, we're just going to assume we're using Kelvin or Celsius here. Okay, so the energy in the thin slice is the thermal energy that is required to raise a unit mass 1 degree Kelvin. Okay, and remember, technically, C of x should depend on U, but we're assuming it's not going to depend on U. There's an exercise. Where you don't you don't assume that it's independent of U. In other words, you use the fact that it is dependent on U, but we're going to assume that it does not depend on the temperature for now. So, anyways, it's the thermal energy required to raise a unit mass 1 degree K. Okay, so what is the mass of the thin slice? What is the mass of that thin slice? Well, it's approximately going to be equal to the surface area times the length, which I'll call delta x. Okay, that gives the volume times the mass density. And this is the area, the cross-sectional area. This is the length of the piece. And again, for a thin slice, we're approximating this as a cylinder. So the volume is just going to be the height of the cylinder, which is delta x, times the face of the cylinder, which is A of x, times rho of x, which is mass density per unit volume. So this is not the linear density. Okay, so then if the temperature of that piece is U of xt, this is its mass, and this is the mass, and this is the specific heat, then what we know is that the total energy, see, if it has temperature U, we know that the total energy of, we know that piece is at, it is U degrees, okay, and we know the mass of it, so it means the total energy of that piece, again, this is only approximate, is going to be equal to C of x times A of x times delta x times rho of x times U of xt. Okay, because the total thermal energy there should be equal to the amount of energy needed to raise that part to its current temperature. Okay, and again, it's important here that we are assuming C does not depend on U. Okay, it's slightly more complicated when C does depend on U. Okay, but we're assuming, if it's U degrees and the mass of the rod, it's U degrees, this is the mass of the rod, and this is the amount of energy needed to raise a mass 1 degree, okay? Well, to get it to go from 0 to its current temperature, that's what this expression is, okay? Specific heat is how much energy you need to put in per unit mass to get it to its current temperature. This is its mass, This is its current temperature. Okay, so the total thermal energy in this piece right here is approximately equal to that. Okay, and we can think about this as a sum. If we sum up over all of the pieces, we would get something like, k equals 0 to n. If we have n slices, it would be c of xk, a of xk, delta xk, which would just be like xk minus 1. Or I guess in this case it would be like xk plus 1 minus xk, rho of xk, u of xk, comma t. And then as n goes to infinity, this sum goes to the integral, and the integral is going to be x equals 0 to L, c of x, a of x, rho of x, u of xt dx. Okay, and then if in addition we do assume that we have constant thermal properties, or better yet, let me just say the rod is homogeneous. If you had a homogeneous rod, then these are all constants, and so this is going to be the integral of rho c a times the integral x equals 0 to L u of xt dx.